very impressed you all got here by 8:30. So, well, welcome back. Kostya to tell us more about integrability in AdS CFT.
So I'm happy to see you again, especially in this early morning. And I'll continue with the sort of general discussion of symmetries of unequal force appearing mills, and in particular the conformal symmetry. So the manifest symmetry of the Lagrangian, when we construct it with the dimensional reduction, is product of the Lorentz symmetry and the R symmetry, which is SO6 for maximally extended supersymmetry. But the Lagrangian also is invariant under scale transformations. Now this invariance leads to enlargement of Lorentz symmetry to conformal symmetry, and it is a general fact, so that in any Lorentz invariant scale, if a Lorentz invariant theory is scale invariant, then it's automatically invariant under larger group of conformal transformations, which I will try to prove now. So the discussion will be general. It well, is not specific to NCL4, and most of it applies to any conformal theory. So the action is invariant under rescalings of X. And simultaneous rescaling of all the fields, so A mu should be rescaled by omega. So all the fields transform according to their scaling dimensions. You can check that the Lagrangian is invariant under these transformations. This is basically a consequence of the fact that there are no parameters of dimension of mass. So the coupling constant is dimensionless. And typically any theory with dimensionless couplings will possess this invariance. Now important point is that this is a space-time symmetry, so the spatial coordinates are just rescaled by an overall factor, and we know that space-time transformations are generated by the energy momentum tensor. So in field theory, so the symmetry transformations are generated by some operators acting on the Hilbert space of the field theory, and so the conserved charges are associated actually with currents. So the currents that correspond to space-time symmetries are all built from the energy momentum tensor. So So this is the current associated with space-time transformation given by some vector field xi. So in particular, if we have a local operator inserted at some point x, let me draw it more carefully. Where is? It's not there. So if we insert an operator at point x, and then the transformation is given by the following equation. So delta xi of O is equal to epsilon, and then limit of r going to 0 of the following three-dimensional integral. So we surround point x by a sphere. So the integral goes over the sphere of radius r. And we integrate the flux of the corresponding current around the sphere. So n mu is the unit vector pointing outwards. And then if you send the radius of the sphere to 0, we get the variation of the operator under this change of space-time coordinates. Actually, proper definition contains a minus here. Now, if the space-time transformation is a symmetry, then the corresponding current should be conserved. So, in the particular case of scale transformations, so if the theory is invariant, under delta x mu equal epsilon x mu, so this is infinitesimal dilatations, then the dilatation current should be conserved. So what does this mean? That this means that if we take the divergence of this current, then we should get 0. So let's calculate this divergence. If we differentiate these two terms separately, then the first term vanishes because the energy momentum tensor is conserved. So only this term survives, and it's equal to the trace of the energy momentum tensor. So we conclude that scale invariance is equivalent to the tracelessness of the energy momentum tensor. So in any scale invariant theory, the energy momentum tensor is traceless. Now, you can check that that is definitely true for n equal 4 superangles, but it's also classically true for, say, pure Young-Mills theory or theory with less supersymmetry, like n equal 1 superangles. Now, the difference is that in quantum theory, the trace of energy momentum tensor has an anomaly. So typically this anomaly is proportional to the beta function, and but for n equal 4 the beta function is 0. So there is some operator identity that identifies trace f mu with beta function times the Lagrangian density, basically. Anyway, in n equal 4 is special in the sense that the scale invariance is not broken by quantum corrections. So the theory remains scale invariant even at the quantum level.
Perturbation theory.
Yes, in principle, yes. To 0 to all orbits. Now, so nevertheless, even in non-conformal theories like QCD, scale invariance plays an important role because its violation is small with the coupling constant. So at weak coupling, conformal symmetry is still a useful notion. So let's study some of its consequences. So first of all, tracelessness of the energy momentum tensor implies more symmetry. So there are more conserved currents. So this is a consequence of Lorentz invariance and symmetry of the energy momentum tensor, because in principle the dilatation transformations and the Lorentz transformations are closed as a group. But nevertheless, the true symmetry group is larger, and this is because if you consider current associated with vector field psi and differentiate it, take the divergence. So again, the energy momentum tensor is conserved. So we can only differentiate the vector field. And then we can use the symmetry of energy momentum tensor to symmetrize the indices on d mu psi, which means that this current will be conserved if psi nu is so-called conformal killing vector. So if it satisfies the following differential equation. k because let's see. Why is that? Well, this is because if this is proportional to the metric, this contracts indices on T min u, and then since the energy momentum tensor is traceless, that will be true. So this is the conformal killing equation. And its solutions form an algebra with respect to the Lie bracket. So if you take the Lie commutator of two conformal killing vectors, then the result will also satisfy this conformal killing equation. Which is basically a reflection of the fact that conformal transformations form a group. So to find all the solutions of this equation, I mean, it's possible. I will just list all of these solutions. So there are several obvious solutions. Constant solution corresponds to translations. So the corresponding conserved charge is just the moment, for momentum, the for momentum. Then if psi mu is proportional to x with the proportionality coefficients that form an antisymmetric matrix, then this transformation generates Lorentz boosts and rotations, and corresponding conserved currents are just Lorentz generators, SO31 generators. So, of course, there is this dilatation generator that we started with. The corresponding charge is the dilatation operator. And finally, there is another set of solutions that are not quite obvious, which correspond to special conformal transformations. So it's a four parametric set of solutions which are quadratic in X. So the corresponding charge will be denoted by K. And so this charge has dimension -1. So okay, that momentum has dimension 1 and K has dimension -1. So it's easy to check, it's possible to check that this is a conformal killing vector. And in fact, this set is complete. So this is the complete set of solutions of the conformal Killing equation. So this vector fields form closed algebra with 15 parameters. And one can check that this algebra is nothing but SO for 2. So the SO31 subgroup of this algebra is manifest. It's just Lorentz transformations. So to get SO42, we need one extra Cartan generator and one lowering and raising operators. And these are precisely translations, or 3 lowering and raising operators, and these are translations and special conformal transformations. So in fact, D is the Cartan generator. So K mu is lowering operator, or negative root, and P mu is raising operator. And the form commutation relations of SO for 2. So these infinitesimal conformal transformations can be promoted to finite transformations. And there is a theorem due to Liouville that conformal transformations are generated by translations okay. Rotations, dilatation, and to that we should add the inversion. And arbitrary combinations thereof. So any conformal transformation can be thought of as a sequence of these basic transformations. So as a side remark, let us see how these transformations are realized in anti-de Sitter space. So if we look at the metric of anti-de Sitter space, then it's possible to see that its isometry group is generated by precisely the same transformations. So it's obvious that it's invariant under translations in X or rotations of X. It's also scale invariant. So if we rescale X and Z by the same factor, the metric stays the same. Now, so inversions are also there. So it's invariant under x mu going to x mu divided by x squared plus z squared, and z going to z divided by x squared plus z squared. A simple calculation shows that this is an isometry of this metric. Now, at the boundary of anti-de Sitter space, when z is 0, this reduces to the usual inversion. So, combination of all of these transformations generate the same conformal group. So the isometry group of AdS 5 is SO42. So this in particular explains how the symmetries of both sides of the AdS CFT correspondence are related. So we conclude that the bosonic part of the symmetries of n equal 4 superrank Mills is actually enlarged to SO42 cross SO6. So the next step is to understand how various observables transform under this symmetry group. And let us consider how the local operators transform. So there is an important class of operators that transform in a particularly simple fashion, and those are called conformal primary operators. Which transform like that. So delta psi O So this operator, the operator can also have Lorentz indices, so it can be a spinor or a tensor. And so this psi menu is the Lorentz generator that acts on the indices of O. So we also assume that this operator transforms in some irreducible representation of the Lorentz group, so it has definite spin. And this is just these rotations in the of this spin indices of O. Delta is a number, and this delta is called the scaling dimension. So in fact, it describes how this operator transforms under rescalings of space-time coordinates. which can be easily seen if we set x to 0 in this formula. So for the operator sitting at the origin, these transformations simplify. So we can just take this formula and specify xi to be one of these transformations from the conformal group. And then we can see how the operator transforms under SO42. So let's consider the case where operator is evaluated at x equals 0. Then P acting on the operator. So for P xi mu is a constant, so only the first term in the transformation survives. So under translations, the operator just translations are realized by derivatives. For Lorentz transformations, only the last term is important. So in the first term vanishes because we put x to 0. In the second term, the divergence of xi is 0 because omega is anti-symmetric. So only the third term is important and is given by some matrix acting on this operator, and this is just this matrix realizes the representation of the Lorentz group. So representations of the Lorentz group are characterized by two numbers, the left spin and the right spin. So if O is transforms as the tensor of S1 S2 type. So the Lorentz group is can be realized as is equivalent to SL2C. So its representations are equivalent to two copies of representations of SU2. So left spin and right spin. So the most general Lorentz tensor can be written as multi-spinner. So it has a certain number of undotted indices, the number of which is denoted by S1, and a certain number of dotted indices, the number of which is denoted by S2. And so sigma is just Lorentz transformations that act on these dotted and undotted indices. Now, if we act by dilatations, so then only the middle term in this equation is important because let's say the last term vanishes because of the anti-symmetry of sigma. The first term vanishes because we evaluate everything at 0. So the dilatations multiply the operator by this dimension. So this scaling dimension is the eigenvalue of the dilatation operator. And special conformal transformations, in fact, annihilate this operator evaluated at 0. Now, if you think of these formulas as defining some representation of this SO42 algebra, then these conditions are precisely the conditions for the highest weight state. So this state O is an eigenvalue of the Cartan generator, and it is annihilated by the negative root, by the lowering operator. And when we act by the raising operator, we get some new state. So the operator, which is the derivative of the original operator. So the derivatives are called descendants. And so this defines the highest weight state in the representation of the conformal group that is characterized by spins and the conformal dimension. So in conclusion, the conformal symmetry is isomorphic to SO42. So all local operators of any conformal theory fall into representations of SO42. So SO42 has rank 3, which means that its irreducible representations are characterized by 3 numbers. So these 3 numbers are precisely this scaling dimension and 2 spins. So these are eigenvalues of the standard Cartan basis of this algebra. And there is a special class of operators which are highest weight in their respective representations. And those operators are usually called highest weight states, or sorry, they're called conformal primary operators. The rest of the states can be generated by repeated application of the translation generator. So they're just derivatives of the highest weight state. So so an operator, in other words, any operator in n equal 4 is either chiral primary or a derivative thereof. So the derivatives are usually called descendants. So let me write down these statements. So all of these representations are infinite dimensional because we can hit any highest weight state by arbitrary number of derivatives. And this is, of course, something that has to be expected because SO42 is a non-compact group. So its unitary representations have to be infinite dimensional. Okay, so therefore, if you want to understand the spectrum of any conformal theory, then we should think of the spectrum as a set of admissible representations of the conformal group or admissible values of the dimensions and spins of various operators. Now, the spins are half integers, so they're sort of discrete labels, but the scaling dimension is a continuous variable. So in other words, what we usually want to do in a conformal field theory is that we want to diagonalize the dilatation operator. So in some sense, the dilatation operator plays the role of the Hamiltonian in a conformal theory. And the statement can be made actually precise if you consider radial directions as our evolution parameter. So then instead of time evolution, we consider evolution and the rescalings. So in radial quantization, the dilatation operator is literally the Hamiltonian. Now let's see what supersymmetry brings in. So the previous discussion applied to any conformal theory. In fact, as long as conformal invariance is an approximate symmetry, this classification of possible operators is still useful. For instance, in QCD, the notion of scaling dimensions or anomalous dimensions is widely used, despite the conformal invariance is broken by the anomaly. Now we want to be more specific and consider this maximally supersymmetric theory, where in addition to this conformal invariance and R symmetry, we also have some supergenerators, which are also global symmetries. So let's see how they match with the conformal invariance. So first of all, since the bosonic symmetries are larger, so there is R symmetry, which is SO6. States or operators can be characterized or should be characterized also by the representation of SO6 or by, well, some extra 3 quantum numbers, which can be sort of a set of 3 angular momenta. So SO6 is a group of rotations in 6 dimensions. So it's characterized by angular momenta. And there is 3 of them, and they can be integers or half integers. Now, another consequence is that many operators become related by supersymmetry transformations. So we can act by a supercharge on some bosonic operator, and it will generate fermions etc. So some operators that some conformal multiplets that are unrelated by conformal symmetry are now become superpartners, and so should basically should not be distinguished because they belong to the same multiplet of the global symmetry group. So so what do we know? How to construct this superconformal algebra? Well, we know that this n=4 theory inherits 16 supercharges from 10 dimensions, and they form this algebra. So this is the standard super algebra in 4 dimensions. Now it is decorated by this extra label that runs from 1 to 4. And basically enumerates all 4 different supercharges of the extended supersymmetry. So since those are parts of the symmetry algebra, we want to know what are their commutation relations with the generators of SO42. Well, we know how supercharges transform under Lorentz group. This is just because they have one spinor index. So we automatically know how they commute with the Lorentz generators. So it's also clear that they have dimension 1/2 because they commute on the momentum, and this means that they are eigenstates of the dilatation operator. So they the commutator of D with Q gives again Q with the coefficient 1/2. Now, but there are also so we know how they commute with this, and they're also translationally invariant. So they commute on 0 with P. The question is how they commute with K. It turns out that we cannot put this commutator to 0, and so we need to, so if we compute commutator of K with Q, well, basically we can combine this index, this vector index into the sigma matrix, and then we have to contract the dotted index with something else. So what can it be? So one obvious guess that it should be Q bar, but that doesn't work because Q has the same dimension as Q bar, but K has dimension -1. So we should write here some new symmetry generator, which is called the superconformal generator. And then the algebra closes. So one can show that the algebra that contains supercharges, superconformal charges, and conformal generator is closed. And okay, so these two equations are enough to calculate all the commutation relations. I will not do it. Instead, I will describe sort of a nice way to realize the superconformal symmetry as a matrix algebra. So let us define a Dirac spinor big theta, which has two indices. So it has so this A is now a Dirac index, which means that it should have two components: the left chiral spinor, which we take to be Q, and the right anti-chiral spinor, which we take to be S. So in terms of components, this is a 4×4 matrix. So this Dirac index runs from 1 to 4. It's a combination of left chiral and right chiral indices. And this SO6 index also runs from 1 to 4. So this is a square 4×4 matrix. And in fact, this matrix forms a bispinor of SO42 cross SO6. Which can be seen by the following, using the following argument. So, so since this is a Dirac spinor, it is natural to introduce the Dirac matrices that act on this spinor in the usual way. And these are just the 4-dimensional Dirac matrices, the familiar 4-dimensional Dirac matrices. But it is convenient to add a gamma 5 to them. So consider a set of matrices gamma mu and add to them I gamma 5. So they form the Clifford algebra in 5 dimensions. So they are SO41 Dirac matrices. In particular, they are commutators are generators of 4-dimensional spinor representation of SO41. Now the next observation is that if we have a set of Lorentz generators and we add Dirac matrices themselves, this set closes under commutations. So gamma mn and gamma m is closed under commutations. Well, it's almost obvious because certainly if you commute two of those, we get just usual SO41 commutation relations. If we commute two of those, we get gamma mn by definition. And when we commute this with this, we get a linear combination of those, which just reflects the fact that gamma matrices themselves form a representation of Lorentz group, so their index transforms under Lorentz transformations, and these are generated by gamma mn. So this is closed under the usual Lie bracket, and it forms four-dimensional representation of SO for 2. So this is just a spinor representation of SO for 2. This is a construction of spinor representation of SO for 2. But now it of course works in any number of dimensions. We could have started with SOD1, and this would still be true. But with 6-dimensional direct matrices, I mean, for SO for 2 there is some extra. So this is a special case. Namely, if you count the number of matrices here, then there is 15 of them. So as a set of matrices, this is a set of 15 traceless 4x4 matrices. In fact, by the usual textbook theorem, this set of matrices is a complete linear basis in the space of 4x4 matrices if their trace is 0. Yes? Yeah.
Which could a priori be in the R symmetry of n equals 4 super.
Oh, it's not there. Just it's not there because it's not a symmetry.
Symmetry of the algebra, but not of the action.
But not of the action. So this is a set of 14 traceless 4x4 matrices, and this is just covers all of them. So, and what is a set of 4x4 traceless matrices? Well, this is just SU4 as an algebra. But here the hermeticity condition is a little different. So it can be shown that all of these matrices, so the Hermitian conjugation is equivalent to conjugation with gamma 5. So they satisfy this conjugation condition. So in this basis, gamma 5 is the matrix with let's see. So it's 1, 1, minus 1, minus 1. So 4x4 matrices with this conjugation condition, traceless, form the algebra that's called SU22. So this construction establishes a canonical isomorphism of SO42 and SU22. So this is one and the same algebra. This is one of these low-dimensional isomorphisms of SO and SU algebras.
Or
no, it's just an isomorphism of algebras. If you think of groups, then one should divide out some central elements. So it's usual. As usual, there is it's like identification of SU2 and SO3. So as groups, they might not be completely same. So up to some global identifications. But as algebras, they are completely equivalent. Now, same is true for SO6, but if you started with Euclidean Dirac matrices. The only thing that changes, in fact, is this conjugation condition. And then we get just literally unitary matrices. So SO6 is canonically isomorphic to SU4. Now, okay, so let me also mention that in this isomorphism, L menu is identified with, obviously, with gamma menu. D is nothing but gamma 5. And then P mu and K mu are 1 plus minus gamma 5 over 2 times gamma mu. So returning back to this spinor construction of the supercharges, we can put everything, all the symmetry generators, in a single supermatrix. So this is an 8x8 supermatrix. And then commutation relations of all the generators just follow from matrix commutation relations of this type of matrices. But it's important to remember that so the supermatrices have bosonic and fermionic blocks. So so by definition, supermatrix is a set of 4 blocks, each 4 by 4. So the diagonal elements are bosonic. And off diagonal are fermionic. So the superconformal algebra is actually can be identified with the matrix superalgebra SU224. So this is the usual. This is the this notations. This notation is used for supermatrices with of definite size. So this denotes the size of the upper blocks, and this is of the lower blocks. And commas denote the rules for Hermitian conjugation. So it's by definition, this is a set of supermatrices such that they satisfy the following rules of Hermitian conjugation. and whose supertrace is equal to 0. Where H is gamma 5, 0, 0, 1, and supertrace of A, B, C, D is by definition trace of A minus trace of B. It can be shown that supertrace is the right invariant that should be used for supermatrices. Okay, so there's one little point that's left over in this construction, namely the supertrace of the unit matrix is equal to 0 as long as there is the upper and lower blocks have the same size. It's quite obvious. So this means that this matrix, that the unit matrix belongs to SU224, but of course it commutes with every element of SU224 being a unit matrix. So so this means that it is a generator of the symmetry algebra that commutes with everything but can appear on the right hand side. So such generators are usually called central charges, and SU224 has a single central charge that indeed arises in the commutators, in the anti-commutators of superconformal generators with conformal with rigid supersymmetries. So commutator of Q A alpha S at B is epsilon alpha beta delta AB and C is 1. So this is central charge. Or I should say that it can appear in the in this anti-commutator, but if you look at this particular field theory realization of this algebra, then the central charge is always 0. So in super-Yang-Mills, central charge is always 0. So of course in any particular representation central charge is a number by Schur's lemma. And in super-Yang-Mills, only those representations in which C is 0 appear. So usually there is people use a special name for the algebra in which central charge is 0. So it is called projective unitary special unitary superalgebra, which is by definition SU22 with central charge set to 0. Now, this algebra has no matrix representations, because if you take these super matrices and commute them, then we inevitably get something on the right-hand side. So in any finite dimensional representation, central charge is not 0. But of course, the representations that we encounter in Yang-Mills are all infinite dimensional. Now, what about the string side? In string side, we also have some supersymmetry. So because we have to consider type 2B string, and type 2B string possesses space-time supersymmetry. So on the world sheet, the world sheet fields are not only embedding coordinates, but also some fermionic fields. And in fact, these fermionic fields can be very nicely described using superconformal algebra PSU22. So to do that, we should understand what kind of description to use for string theory. Well, yes.
I mean, is there any physical reason why you should have C equal to 0 in supersymmetric angles?
Let me think about it. There should be some. I can't come up with any simple explanation, but let me think about it. Okay, so what is string theory in the most simplest terms? String theory is a theory of embeddings of a two-dimensional surface into some manifold. Now, superstring theory, well, obviously is a theory of embeddings of two-dimensional surface in a supermanifold, although usually we use a different description when supersymmetry lives in two-dimensional world sheet. It's called RNS formalism. And the space-time supersymmetry is an emergent phenomenon. It's not very obvious from the beginning. People haven't managed to use RNS formalism in AdS 5 x S5. The technical reason for that is that there is a Ramon-Ramon flux, which doesn't fit very well with RNS formulation. So this formulation of the world sheet living in superspace, which is called Green-Schwarz description, seems to be more appropriate. And then we need just to understand what is the AdS superspace. So, and here this superconformal symmetry seems to be very useful, because if you look at the bosonic constituents of this background, then they're all cosets of the R symmetry group and of the conformal group. So the sphere is surely very well known that the sphere is a coset of SO6 over SO5. Now, AdS 5 can be represented as a coset of SO for 2 over SO for 1. Now it is homogeneous space with SO for 1 being its isometry group. To see that the SO for 1 is the denominator of this coset is well, it's relatively easy thing, but I will not do it. So anyway, so this is we can represent both of them as cosets. So the corresponding superspace is obviously a coset of this superconformal group with the same denominator. So in particular, PSU224 is the global symmetry group of string theory, and the set of string states is characterized as a set of representations of this group. And which is defined by the same set of labels as the set of local operators in Zuckerberg-Mills theory. So the question is how to find this spectrum on both sides and to see how the spectrum interpolates from Victor-Strong coupling. So okay, that's it for today, and next time I'll start with much simpler and less algebraic discussion of how to define the scaling dimension in Zuckerberg-Mills theory. Thank you.
Questions? Thank you.
When you grew up to your supermatrix with SU22 in the top left and SU4 in the bottom right, were those to represent different sort of matrix of generators of those two groups, or was it something different?
The matrix of generators is just, okay, these are numerical matrices. So they're numerical in their diagonal blocks. Off diagonal blocks are sort of numerical fermionic, so they have Grassmann entries. And commutation relations are just, you take these matrices, multiply them as matrices, and then subtract the multiplication in different order. So it's, yeah, like SU2 is a group of 2 by 2 matrices with respect to multiplication, with respect to anti-commutator. Yes?
When you introduced the central charge, was that a property of the symmetry algebra, or was it actually a property of the conformal field theory?
That was the property of this matrix representation. So if you want to think of this as a matrix algebra, then it has the central charge. But if you think of it as an abstract algebra, then study its representations, that only those representations in which central charge is 0 do appear. It's like SU2 is, as an algebra, SU2 is a set of 2 by 2 matrices. But then in physical applications, it can be represented by 2s cross s, 2s plus 1 squared matrices, and so that have the same commutation relations. So these supercharges have the same commutation relations as entries of this as this 8x8 supermatrices, apart from the central charge.
Any more questions? Any question again?